Section 8.3 Applications to Physics and Engineering. In general, the hydrostatic force exerted on a thin plate with area a square meters submerged in a fluid with density ρ kilograms per cubic meter at a depth d meters below the surface of the fluid is F equals m times g, which is ρ times g times a times d, where m is the mass and g is the acceleration due to gravity. The pressure P in pascals on the plate is defined to be the force per unit area, where P is just F divided by A, which is ρ times G times D. Let's do an example. A dam has the shape of a trapezoid shown in the figure. The height is 20 meters, and the width is 50 meters at the top and 30 meters at the bottom. Let's find the force in the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. So how about we put in an x-axis here? Let's see if I can cut through. So remember, our depth is below the surface of the liquid. So we should probably start the x-axis where the liquid starts, around over here. So let's make that 0 at the top of the liquid, which is, 4 meters from the top of the dam. So that means that the top of the dam over here in this corner is at -4 on the x-axis. So let's take a look at an arbitrary little rectangle. We'll chop up all of the water so that we can see the pressure on a single plate of water and then add those up. So what I mean is, how about we draw like a little bit better, maybe it would be nice. Okay, so this is roughly a rectangle. It has some tiny width, delta x. So I'm chopping up the water. I'm going to do a whole bunch of these rectangles, basically, to the point where I take the limit as the number of rectangles goes to infinity, and I stack them all up, and that'll give me the total force on the dam due to hydrostatic pressure. So first I need to find the force for one of these rectangles, and then I can find the force in the total force. So this rectangle is situated at some depth, which is, let's say, a sample point from the water levels. So let me draw a little bit more. Let's make the sample point at the midpoint. So we'll call that sample point xi star. That's how deep it is to the plate that I cut in. And let's see if we can find out the area of that little rectangle. Well, from here to here is 30. So that means that if I chop up the trapezoid into a triangle and a rectangle, then from here to here is 15, because that matches with the 30 on the bottom and it's half of it. So over here, there's some missing piece, which is the piece of this triangle. Let's call it A. So I have to figure out what A is. Well, on the top, it's also 15 over here. And over here is how much left I have. Remember that I covered it up a little bit, but the top was 50 because the width of the top is 50. So if this is 15, then the missing piece in the top must be the missing part of the half of 50, because altogether this must add up to 25. So this must be 10. And then the other piece over here would be 15, and then another 10 would be 50. So let's see if I can draw all of that separately. Okay, so this triangle is this triangle right over here. And that means that the top is 10. And the height of the triangle is 20. Because that's this 20. So then I've got this rectangle that cuts through. and it's A over there. And that's this A. So if from here to here is xi star, and from here to here is 16, because remember we started at 0 and the height is 20. If I go to the top, that's at -4, so this is 4 away, this little bit over here. So the water is just goes down 16 meters deep. So that means that if I look from xi star, which starts at 0, all the way to wherever the bottom is, then that would be a total of 16. So if I want to figure out what it is just below xi star, that'll be 16 minus xi star. Okay, so then if I took 16 minus xi star over here, I added to xi star, and I added 4, then I would get all the way to 20. You can imagine that the water level is like cut off somewhere over here, just like over here. Okay, so let's use similar triangles to solve for A, because we want to write everything in terms of x. So we have this part of this triangle divided by this part of this triangle must be equal to the bigger part, 10, divided by 20. So A over 16 minus xi star must be equal to 10 over 20. So we just cross multiply, solve for A. We get that A is equal to 16 minus xi star over 2. And we just divide and we get 8 minus xi star over 2. So that means that if I want to call the width of this thing, how about Wi for the ith plate, then Wi is 2 times 15 plus A, because I take 15, I add it to A, and then I duplicate it to get the entire width. So just expand out, that's 2 times 15 plus 8 minus a half xi star, because we solve for what A is, and that's just 46 minus xi star. So that means I can get the area of one of those plates now. Just multiply by delta x. So the width times the height delta x is equal to 46 minus xi star delta x. So now I can get the pressure, because the pressure on this ith plate is approximately, remember it's rho times g times d. So I need to take the density rho of water. Well, the density rho of water, as we've seen before, is 1,000 kilograms per cubic meter. So I'll take 1,000, I'll multiply it by g, acceleration due to gravity, and I multiply it by my depth, how far I go deep, and that's just xi star. Now that I have the area of one of these plates and I have the pressure, I can figure out what the force is, because I can just take pressure times area and I can get the force. So let's do that. Force will be pressure times area, which is about 1,000 times g times xi star times 46 minus xi star delta x. So this is for a single one of these plates. Now, like I said, I'll take the limit as the number of these plates goes to infinity. So that'll be the total force F. So the total force is the limit of this sum of 1000 times g times xi star times 46 minus xi star times delta x. And that becomes the integral from 0 to 16. Because remember, I start at 0 and I only go down to 16 because that's how much the water is. I'm not doing the entire trapezoid. I'm only starting where the water is. So I get 1000 g, and then xi star becomes x, and we get 46 minus x dx. Because remember, it doesn't matter where the sample points are when you convert to the integral. When you take the limit, you can take the sample points anywhere. So that's 1000 times acceleration due to gravity is a constant 9.8. So that's what g is. And then the integral from 0 to 16 of 46x minus x squared dx, which is 9800 times 23x squared minus x cubed over 3. And we take our antiderivatives. And evaluating that from 0 to 16 gives us about 4.43 times 10 to the 7th newtons. Let's find the hydrostatic force in one end of a cylindrical drum with radius 3 feet if the drum is submerged in water 10 feet deep. So we'll try drawing our drum. Similar to before, we will draw what's going on, and then we will cut up the cylindrical drum into lots of little plates, and we'll look at the force on one of those plates, and then we'll stack them all up. So this is, let's see, if the circle is radius 3 feet, we might as well just put it at the origin and say that this is the equation. Oops. X squared plus y squared equals 9. Make it a little bit easier. So this thing is submerged in water 10 feet deep. So the bottom of the circle should be at 10 feet. So if I go up, this distance is 10. So it goes a little bit past the circle because notice the circle has a radius of 3. So that means from here to here is 3. From here to here is 3. So from top to bottom is 6. So the water is 4 feet above. So that means that if I want to look at from the middle of the circle to the top, that would be a depth of 7. Because from here to here is just 3. So let's try drawing one of these little guys. How about over here? Just going to cut up one section of the drum. And I'll say that it has a little height, delta y, because I'm stacking it up along the y-axis this time instead of along the x-axis. So that means that the distance to my little plate is going to be yi star this time. I don't like how that arrow at the bottom came out. Let me try doing this a little bit better. Put the I don't know if that made it any better. Okay, so I would like to know the depth in order to figure out what my actual pressure is going to be. So I should figure out that from the top of where the water starts all the way to my plate, how much that's going to be. So from here to here is 7. From here to here is yi star. Then that means that the distance or the depth that this thing is submerged, is 7 minus yi star. So that's from here to here. Let's see if we can figure out the area of the plate then. We can figure out the area, multiply the area by the pressure, and we'll be good to go. So the area is length times width, or, you know, the base times the height. Well, this thing is just the x value. The x value we got in the circle, if we solve x squared plus y squared equals 9, and we only solve for the positive part, then that'll be the square root of 9 minus yi star squared. So that means that ai is 2 of those for the length, and then we multiply by height. So it's 2 times the square root of 9 minus yi star squared times delta y. Now I need to find the pressure on the ith slab that I've cut over here. So let's go back to our formula for pressure. Remember that that's rho times g times d, where rho is the mass density. So g is the acceleration due to gravity. I could rewrite this as delta times d, where delta is the weight density and d is the depth. So if I can use the weight density of water, then I can just multiply it by the depth, and I'll be able to find the pressure. The weight density of water is delta equals 62.5 pounds per cubic foot. So that means that the pressure is approximately delta times the depth. So that's 62.5 times how far I go down, which we said is 7 minus yi star. So I'll just throw that in there. Now that I have area and pressure, I can find force. So the force on the ith plate will be the pressure times the area, which is approximately 62.5 times 7 minus yi star times 2 times 9 minus yi star squared times delta y. And you already know what I'm going to do next. I can now take my limit and get the total force. So the total force is the limit of the sum of all of these plates as I sum up more and more and more of these plates. Not just the area of the plate, obviously I'm taking the entire force on each of the plates. So I get 62.5 times 7 minus yi star times 2 times the square root of 9 minus yi star squared delta y. And that becomes an integral. I'm going to take 62.5 times 2 and pull out, so 125. And then I've got the integral. Well, I only want to integrate over the drum. So the drum goes from here to here. So that's, if I think about the origin over here, then that means it's going from minus 3 to 3. So go from minus 3 to 3. I'm stacking these things up along the y-axis. So everything's in terms of y. That's why I use delta y. So that means that I have 7 minus y times the square root of 9 minus y squared dy. So let's distribute the 7 and the y. So we get 125 times 7 times the integral from minus 3 to 3 of the square root of 9 minus y squared dy minus 125 times the integral from minus 3 to 3 of y times the square root of 9 minus y squared. Well, this integral on the right is just great because this is a symmetric domain and this is an odd function in the integrand. So that means that this entire integral is just 0. Because when you integrate an odd function over a symmetric interval, it just disappears. So I only have to worry about this integral. So how about I write that out? 125 times 7 is 875. And this is the only integral I have to evaluate. So if you wanted to, you could do a trig substitution here, but I think it's a little bit easier if you just think about what you're integrating over. This drum is just a circle. So the integral from minus 3 to 3 of the square root of 9 minus y squared is just the area of a circle. It's only the positive square root though, so it's only a semicircle. So if I want to get this integral, I'll just take 875 and I'll multiply it by the area of a semicircle, which is half pi r squared. This circle has a radius of 3, so it's half pi times 3 squared, which is 7875 over 2, which is approximately 12,370 pounds. In general, for a system of n particles with masses m1, m2 through mn located at points x1, x2 through xn on the x-axis, the center of mass x bar is the point on which a thin plate of any given shape balances horizontally, and it can be shown to be the sum of the masses of each of the points times each of the points divided by the total mass. So we say that mi, xi are the moments of the masses mi, and m equals the sum of all of those moments, of all of the mi's, all the masses, is the total mass of the system. The sum of the individual moments is called the moment of the system about the origin. So this is in the one-dimensional case where we just have one axis. What about if we have a system of particles located in a two-dimensional space at all of these different points? Well, then we can still define our moments. In this case, we define moments of the system about the y-axis and about the x-axis, and we do that separately. So the moment about the y-axis is the sum of all of the masses of all those points times their distance from the y-axis. Notice that this is the moment about the y-axis, but you're summing up a whole bunch of x's, so it looks a little bit like it's backwards. But it's really not backwards, because the distance from the y-axis is horizontal. So that's a certain x distance away. Similarly, if you want the distance from the y-axis, you have to sum up y values, because when you go away from the x-axis, you go a certain distance y. So in order to find the center of mass, you need the coordinates x bar, y bar. As before, you take the sum of all of the masses times their distance from the center, and you divide by your total mass. So if we want to find the coordinate of x bar, we have to find the distance of x bar, the distance of the point away from the y-axis, multiplied by the mass, add up all of those, that's our moment of about the y-axis, and divide by the total mass. Similarly, for y bar, we have to figure out all of those y distances away from the x-axis, how far away we are from the x-axis, and then we multiply by all of those masses, and we divide by the total mass. So let's do an example of that. Let's find the moments and center of mass of the system of objects that have these masses and these points. So let's look at the moment about the y-axis. So we need the mass 3 at the point minus 1, 1. So this is about the y-axis. So how far we are away from the y-axis is a distance x. So we'll multiply by the x value over there. And then similarly, the next mass is at 4, and that's a distance of 2 away from the y-axis, plus 8, a distance of 3 away from the y-axis. Altogether, that's 29. And similarly, the moment about the x-axis, we take each of the masses again, 3, 4, and 8, and we multiply how far away we are from the x-axis, which is the y value. So 4 times -1 and 8 times 2. All of those y values, and we get 15. So now let's get the total mass so we can divide and find the center of mass. So the total mass m is the sum of all the masses. That's 3 plus 4 plus 8. We only had 3 points, so we only have 3 masses. So that we look at the x-coordinate of the center of mass, x bar. That's the moment about the y-axis divided by the total mass. So that's 29 divided by 15. Similarly, y bar is the moment about the x-axis, because it's how far we are from the x-axis in terms of y, so that's 15 divided by 15. No, I should have probably wrote this equals 15. Yeah, so that's just 1. So that means that our center of mass, x bar, y bar, that point is at 1 and 14/15, comma 1. So in that example, we just looked at a couple discrete points. What if you had an entire lamina where you have infinite number of points and they all have, masses in there? So then it would be great if we could find the center of mass, right? So what we can do is define the x-coordinate of the center of mass to be 1 over the area times the integral of x f of x, and the y-coordinate to be 1 over the integral times half of x squared. So you might be thinking, okay, well, how did you get that? Well, you would expect that x bar is the moment about the y-axis divided by the total mass, right? Well, the moment about the y-axis, that should be the sum of the distance from the y-axis, the x value, times all of the masses. So the masses for every single one of these points, let's see if we could find one of those. Well, you'd want the area of one of these little rectangle cutouts times its density. So if this thing has density rho, let's see if we could figure out what the area of a single one of these guys would be. Well, it has a tiny little change, delta x. So the width is delta x. So what's the height? Well, the height of this thing is just the y value. That's f of x. So that means that if I were to write an integral, it would be the integral from a to b of my distance x times my mass, which is rho f of x dx. F of x dx is the area of one of those little pieces. Rho times f of x dx is the mass, and then the x value is the distance away. So this is just mass times distance from the y-axis, same as it was before. And then I just take this and I have to divide by the total mass, which is the density times the total area. Notice that the rho on the top can be taken out and cancel with the rho on the bottom. So that's how I can end up with this integral right over here. Because there's not going to be any rows, we just have x f of x dx divided by a, which is 1 over a. Similarly, if you want to get the coordinate of the center of mass, the y-coordinate, that would be the moment about the x-axis, how far away we are from the x-axis, divided by the total mass. So that would be the integral of, well, we need to figure out what this distance from the x-axis is now. Notice that if I wanted the distance to the y-axis, that was just x. But it will not be the same as if I want the distance to the x-axis. That's not just y. In this case, it's half of y. because I want the distance from the center of mass for this little cutout that I'm doing, that I'm going to stack up. So that means that I need to make sure to multiply by my distance half of y. And then again, the area is just rho times f of x dx. Well, the mass is rho times f of x dx, the area is f of x dx. So then y is f of x. So this is the exact same thing as just saying half of f of x squared, which is where this comes in. And as before, the rho will cancel out in top and bottom. So we just have to divide by rho times a, and then we get this. So one last thing to mention, the symmetry principle says that if R is symmetric about a line L, then the centroid of R lines on L. So if we have something nice and symmetrical around both sides, then we can figure out either x bar or y bar pretty easily if it's, symmetrical about the x-axis or the y-axis. Let's find the center of mass of a semicircular plate of radius r. So we'll draw our semicircular plate. Maybe it looks something like this. Here's r, here's minus r. Here's my x-axis and my y-axis. So this is y equals the positive square root of r squared minus x squared. And let's see if we can figure out where the center of mass is. Well, in this case, f of x is the square root of r squared minus x squared. And a is going to be minus r, and b will be r. That'll be what I integrate from. So by the symmetry principle, one of these guys is nice. The x-coordinate of the center of mass will just be 0, because it has to be on the y-axis, assuming that, you actually believe that what I drew is symmetrical, because it's the same on the left as it is on the right. So that means somewhere over here will be our center of mass. We just don't know what the y-coordinate is, because it's not symmetrical up and down. So let's get at our total area so that we can divide by it. Our total area is the area of half of a circle, so that's half of pi r squared. And now we can get that y bar is 1 over that area times the integral from minus r to r of half of f of x squared. So that's 1 over half pi r squared times, well, this integral over here. So I'll pull up the half from half f x squared dx, and I get the integral from minus r to r of the square root of r squared minus x squared. Squared, almost forgot. Which is really nice, because that way I don't have to deal with that stupid square root. So I get 2 over pi r squared times the integral from 0 to r, because this interval from minus r to r is symmetrical, and this is an even function, so I can just go halfway and double it. Make it a little bit easier to evaluate. So that's just 2 over pi r squared times r squared x, because r is constant. To think of it as like 3, and then you get 3x when you integrate, take the antiderivative, and then we get x cubed over 3, and we evaluate that from 0 to r. So that's just 2 over pi r squared times 2 r cubed over 3, which is just 4r over 3 pi. So that means that our center of mass is x bar y bar equal to 0, comma 4r over 3 pi. So it's somewhere over here in our picture. if you want to look at it. That's the point 0, 4r over 3 pi. Let's find the centroid of the region bounded by the curves y equals cosine x, y equals 0, x equals 0, and x equals pi over 2. So the area is just the area underneath the curve cosine from 0 to pi over 2, so let's get that out of the way. We get the area from 0 to, the integral from 0 to pi over 2 is the area. So that's integral of cosine x dx, which is just sine when we take the antiderivative and we evaluate that from 0 to pi over 2. Sine of pi over 2 is 1, sine of 0 is 0, so we just get 1 minus 0, which is 1. And then x bar, let's get that. So that's going to be 1 over our area times the integral from 0 to pi over 2 of x f of x dx. So that's just the integral from 0 to pi over 2 of x times cosine x dx, which is just x times sine x from 0 to pi over 2 minus the integral from 0 to pi over 2 of sine x dx, because we use integration by parts. Whenever you see a product like this, it's usually good to use integration by parts. You just let u equal x, and then dv equals cosine. So then v is sine, so u times v is x times sine x, and the integral of v du is just the integral of cosine dx. Sorry, it's just the integral of sine x, because dv was cosine, so v is sine. Integrating v means integrating sine. And this just ends up being pi over 2 minus 1. So let's get y bar now. That's 1 over the area times the integral from 0 to pi over 2 of 1/2 f of x squared dx, which is 1/2 of times the integral from 0 to pi over 2 of cosine squared. You might remember that we integrate cosine squared usually using a half angle identity because it's the easiest. So we'll just go and replace this with 1 plus cosine 2x. So then we get 1/4 times x plus half sine 2x from 0 to pi over 2, which is just pi over 8. So that means that the coordinates of our centroid, our center of mass, are 1/2 pi for x, minus 1, almost forgot the minus 1, and 1/8 pi. If we try drawing this. Couldn't decide if I really wanted to, but I will. Okay, so that's cosine, very roughly. And it intersects the x-axis at pi over 2. And our centroid is around over here at pi over 2 minus 1, pi over 8, as we just calculated. If the region R lies between two curves, y equals f of x and y equals g of x, where f is bigger than g, then the centroid is x bar, y bar, where x bar is now x times the difference. That makes sense because, you know, we just replace the f of x dx with f minus g, because that's how we got the areas between curves to begin with. This one looks a little bit more confusing, though, for y bar. So let's see if we can see why that one makes sense. Well, the new distance from the y-axis is still just the x value. So that's where this x comes in. But now the distance from the x-axis is no longer just half of the y value. In this case, we have to figure out what the center of this thing is, which is the average of the two y values. So we have to look at the y value over here, the y value over here, go halfway in between. So use the midpoint formula. We get half of the y value of f and half of the y value of g. So that's how far away we are from the x-axis. So that means that's what gets plugged in. So we get that y bar is equal to 1 over a times the integral of half of f of x plus g of x. That's how far we are from the x-axis. And then we multiply that by f of x minus g of x. So I'll put that also over there. And then notice what happens here. When you FOIL this out, there's 1 plus and 1 minus. The middle terms will cancel, which makes sense because this is a difference of squares. So when you FOIL this out, you get exactly this. So now it should make a little bit more sense why the y bar is slightly different. Let's do an example though. We'll find the centroid of the region bounded by the line y equals x and the parabola y equals x squared. So first we should probably draw what's going on here. So we've got the parabola y equals x squared, the line y equals x. Maybe I'll do a parabola first. Wow, pretty bad parabola. Okay, let's see if I can get the line any better. No, both pretty bad. All right, so this line on top is y equals x. And the parabola underneath is y equals x squared. Remember, they intersect at 1, 1. You could just solve them, set them equal to each other, and at 0, 0. So we want to find the centroid of this region. We need to find the area first. So let's set f of x equal to our top function, so that's just x. G of x will be our bottom function, so that's x squared. And then we're integrating from a equals 0 to b equal 1. So our area is just as normal. It's just the area between the two curves. So we just subtract f minus g, and we get x minus x squared. So that's easy to integrate. X squared over 2 minus x cubed over 3. And we evaluate from 0 to 1, and we just get 1/6. So now let's find our center of mass. So let's look for x bar first. So that's 1 over the area times the integral from 0 to 1 of x times the difference. So let's go and subtract these guys. We get 1 over the area, that's 1 over 1/6, times the integral from 0 to 1 of x times x minus x squared dx. We multiply out, and we get 6 times the integral from 0 to 1 of x squared minus x cubed dx. So that's just 6 times x cubed over 3 minus x to the 4th over 4. And we evaluate, and we get 1/2. For y bar, we take 1 over a, multiply by the integral of 1/2, and then we have to do the difference here of f of x squared minus g of x squared. So it becomes a little bit different. We get 1 over 1/6 times the integral from 0 to 1 of x squared minus x to the 4th. So that's just 3 times x cubed over 3 minus x to the 5th over 5, which is just 2/5 when we evaluate it. So that means that our centroid, our center of mass, is 1/2 2/5. So it's like somewhere over here. Roughly. Point like it. There we go. So 1/2 2/5. So it turns out that there's a cool connection between solids of revolution and centroids. If R is a plane region that lies entirely on one side of a line L in the plane, and then R is rotated about that line, then the volume of the resulting solid is the product of the area and the distance d traveled by the centroid. So let's be a little more clear when we do an example, I think. Let's say we take a torus and we form it by rotating a circle of radius r and but a line L in the plane of the circle that is a distance big R from the center of the circle. Let's find the volume of the torus. Okay, so now you're really gonna cringe when you see this drawing. So here's my donut shape, my torus. Okay, so it's supposed to look like a donut. It's nice and three-dimensional, maybe. And we have a circle over here. So you get that by basically just slicing the torus. So the circle has a radius little r. So we cut up a tiny little cross section of, well, not necessarily tiny, I don't know, we just do a cross section of the donut and we get a circle. However, the donut itself on the outside has one big circle. So that big circle has a radius of r. But it's a big R because it's different than the radius of the small circle. So we form the torus by taking this little circle and we drag it all along. We drag it all the way around R until the circle travels all the way around and forms the torus. We just like pull it along. So now if we want to get the volume, the theorem of Pappus says that we just have to track the centroid and see where that travels. So first let's get the area of the small circle. The area of the small circle is just pi times little r squared. The centroid is just the center of the circle. I should probably write circle of radius r because there's two circles, so I should specify which one I'm talking about. And then I want to know how far it travels when I drag the circle along to trace out the torus. It's kind of like if you had just like a circle and then you waved it around to rotate in the air, you could like see the path. If you moved fast enough, it would trace out this donut shape, even if you only started with the circle to begin with. So how far does it travel? Well, it moves all the way along this circle of radius r. So that means that this thing is traveling the entire circumference of the big circle of radius r. So the distance traveled is just 2 pi r, but it's a big R. So now theorem of Pappus implies that the volume of our donut, the volume of our torus, is A times D, area times distance traveled. So that's just going to be 2 pi times big R times the pi r squared, our area. So that's just 2 pi squared r squared r.